Hey folks, this is Captain Jones here to talk to you about how to share data wisely between interrupts and user programs. We're going to talk today about how we can do that to write interrupt service routines that do more useful stuff to us than we've seen previously. And we're also going to show you how, under certain conditions, the sharing of that data might result in something called a data race, which is a subset of a race condition. And so once we identify, where those might occur, we'll show you how to actually share data to do useful things in a safe way that doesn't open up the possibility of a data race. All right, so let's get started. Okay, so to start, I'll just say, so far our interrupt service routines have not done a whole lot. They've really just, sort of taken something from, the keyboard and echoed it to the display, which doesn't involve a whole lot of interaction with any other user program. But interrupt service routines can be really useful, particularly when they are able to kind of start sharing pieces of data with the user program. So I'm going to come up with a couple examples of how we might do that. We'll take, this is sort of a depiction of two programs here where we're trying to use an interrupt service routine to display some useful piece of information. So we'll assume that there's this variable count that the ISR and the user program are both going to reference. Whenever the keyboard ISR runs, it's going to load the count value into a register. It's going to add one to it, and then it's going to store that back into the count variable. And our user program is going to, in an infinite loop, sort of wait for 1 second to pass and then display to the screen that X number of keys have been pressed since the program started running. Doesn't do anything super useful, but it does demonstrate how we might sort of send data back and forth between these two programs. And so the first thing I want to show you is how we're actually able to reference the same variable from two different programs. If you try to do this in using just kind of our normal load instructions, you run into the fact that these only really work, well, at least load and load indirect only work within some sort of range of the program counter. And so if my interrupt service routine is all the way down in memory 0500, and my user program is at least 3000 is the first address of the user program. There's no offset big enough that I could put into that instruction for the program counter in either program to access a variable that's written in the other program. So the way I do this is I'm going to define the variable in one program, and then in the other I have to define basically a pointer to it. In this case, in the user program, I'm going to define the variable count as an empty space in memory, one word long. And then in my interrupt service routine, I'll define a variable called pointer count, PTR short for pointer, that gets the value of this variable. So when the assembler runs, it'll identify where in memory this variable is. It'll store the address of that variable, the memory location of that variable right here. So pointer count has the memory address of this variable. And what that does is it lets me use the load indirect and the store indirect instructions to be able to access this variable here in my user program, kind of indirectly through its address. If I wanted to, I could have had this flipped around, so I could have defined count in my ISR and then accessed it with loads and stores and done the sort of pointer count on this side. They're roughly equivalent. So number one, that's kind of how that's the little trick we got to do to be able to access the same variable from two programs that are in widely different spaces in my my memory space. This program is an example of, you can see here how I've got an ISR, my service routine, that is writing to this variable and also reading from it. And my user program, very intentionally, is only ever reading from this variable. And so by virtue of the fact that there is only one piece of software, one program that is writing to this variable, this is an example of a situation where I don't need any synchronization. I don't really have the possibility of a data race. I'm safe to write code in this fashion. and that has some caveats, which I'll mention briefly later. Where I kind of might run into issues is it in this scenario where I've got both my ISR and my user program that are trying to write and read from a variable at the same time. So we're going to modify our example slightly. We'll say that I've got a variable now here called enter flag, and so in the interrupt service routine, when this runs, we'll have it written so that if it was the enter key that was pressed, so if the data register has hex A, which is the ASCII code for the enter key, then it will increment this variable called enter flag. So every time the user presses enter, this variable sort of ticks up 1. The user program in an infinite loop is going to check that flag. And as long as that value is greater than 1, it will show the message enter pressed onto the screen, and then it will decrement that variable. Excuse me. So what this allows us to do, hopefully, is that we display the message enter pressed as many times as the enter key is actually hit by the user, and by setting the code up like this, the user can hit the enter key multiple times while maybe it takes a long time for the display to show this variable or display this message. While it's being displayed, the ISR routine can be sort of incrementing this flag if the user is pressing the enter key multiple times, and those aren't necessarily lost. They're eventually there'll be a one-to-one correspondence of keys pressed and messages displayed by using this flag. Now we run into a problem though if we write our code like this, which I'll demonstrate right here. Let's imagine that I've got these 3 lines of code which are decrementing my variable. So I'm loading the enter flag variable into R0, I'm subtracting 1, and then I'm going to try to just store that back in my variable. Let's imagine that while that's occurring, at the same time, my ISR runs. So in this case, we'll imagine the enter flag has the value 5. So it gets loaded into R0, I subtract 1. So R0 was loaded with 5, the value of enter flag. It gets 1 subtracted from it, so R0 has the value 4. Before it can update the enter flag variable, my ISR runs. These lines of code are trying to increment that variable. When the ISR grabs the value of enter flag, it's still 5. So it gets incremented and stored back. Enter flag has the value 6, which is 1 more than it had previously, representing the fact that this ISR is run. The user code, though, has no knowledge of that. It was operating on an old value of enter flag. Recall that R0 has 4 back in our user program. So when I execute this store instruction, the enter flag variable gets overwritten. It was 6, now it's 4. And what I've effectively done is, sort of ignored my interrupt service routine. I've acted like it never existed. I totally missed the fact that the user pressed the enter key by virtue of this, this little race condition. And this is actually a specific type of race condition called a data race, because the ordering of this code has caused erroneous behavior, specifically causing a piece of data, the enter flag variable, to get an incorrect value. So what we can kind of learn from this is that when I've got 2 programs that are both writing to the same variable, that's a critical section. Anytime I'm sharing or I'm reading and writing to from shared data from 2 places, that's basically a critical section. And so just like in my race conditions lesson, what I need to do, the easiest thing to do is to disable interrupts sort of before and after. So you can see here I got some updated code where instead of just sort of blindly decrementing my variable, now I am inside my loop. When I go to do that, I'm going to disable my interrupts first. Then I'm going to decrement my code. So this section here, this critical section, is guaranteed to complete. And then I will re-enable interrupts before branching back to my loop. And this this will run correctly. This will make sure that enter flag is only ever incremented once and decremented once, and I don't find myself in this situation here where I'm getting erroneous values. Okay, so to summarize, there are lots of really useful ways to use interrupt service routines, particularly when they start sharing data or sort of sending information to user programs. The general way to do that is to define a variable in either the user program or the ISR, and in the other one to define sort of this pointer to that variable or address of that variable, and use the load store indirect instructions to access that variable directly. If there's just a single writer to that variable, then more or less we don't need any synchronization. There's no possibility of a data race. However, when we have both the ISR and the user program that are trying to write to that variable at the same time, that's when we have the possibility of a race condition, specifically a data race. And so in that case, updating the shared data, reading or writing from it, is effectively a critical section. And so we need to disable interrupts and enable interrupts before and after. This is a little oversimplified. Don't forget that if we're doing this really correctly, we should be not necessarily disabling interrupts, but getting the current process PSR status or global interrupt enable status ahead of time, disabling and then restoring that if there's a chance that we so that we don't actually enable interrupts that maybe were previously disabled. And by doing that, we can make sure that we are accessing this piece of shared data safely. All right, folks, that's all I got. I'll see you next time.